Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to provide an example of how to use trigonometric substitution to evaluate integrals of appropriate form. And again, let's talk about what I mean by appropriate form. We're going to take a look at this is example number 14, section 8.4 in your text here. I always give people this advice. If you see something that looks like Pythagorean theorem, like the square root x squared minus 1, or reminds you of Pythagorean theorem, that's a good indicator that trigonometric substitution may be a good way to hit this integral with. I always start by writing out sine squared theta plus cosine squared theta equals 1. Then I use this to guide my choice for the substitution here. Now what I'm looking at here, we have an x squared minus 1 here. There's no minus 1's anywhere. I could move this minus sign to the left, but then I'd have to move something to the right. I'd end up with another minus sign. What I'm going to do is take this equation and divide everything by cosine squared to get a different form. So this is going to read tan squared theta plus 1 equals secant squared theta. And now, looking at this form, it's pretty easy to just take this 1 and move it over here. This now reads tan squared theta equals secant squared theta minus 1. And now when I compare this to this, they look pretty darn close. So I'm going to start with a substitution of let x equal secant theta. And again, it's important to understand why this will work. Why would we do that? Because x squared minus 1 now will equal secant squared theta minus 1. And as I look over here, that's equal to tangent squared. And then square root of that will be just tangent. So that will simplify this right down to something I can deal with a little bit easier. All right, now, to make the substitution, however, we're going to need the dx. So the derivative of secant is secant tangent. And if you don't remember that, write this 1 over cosine and apply the quotient rule. So this is going to be secant theta tan theta d theta. I'm going to go ahead and make my substitution here. This doesn't have limits. If it had limits, I would write the appropriate limits out and find the appropriate values for theta, but this one doesn't. So then we're going to have integral 2 times dx, which is secant theta tan theta d theta, over x cubed, we got to get that taken into account, so that's going to be secant cubed theta times the square root of secant squared minus 1 equals. So now I've just made my substitution, calculated my dx, sub those values in, being very cautious. While I'm at it, this 2, I'm going to go ahead and bring that out in front of the integral. Secant over secant cubed. That's going to give me a 1 over secant squared. Again, that's a square. This tangent we'll leave alone for a moment. Tan theta d theta. And then square root of secant squared minus 1. That's secant squared theta minus 1. As I look over here, secant squared theta minus 1 is tangent squared. So I'm going to go ahead and write that out. Tangent squared theta. Right, equals 2 times the integral of. All right, so now, as we look at this, square root of tangent squared is tangent. So these actually cancel. And this is a secant squared. And secant is 1 over cosine. So let's write that cosine squared theta d theta. All right, now, now we've got this down to something that hopefully we can handle. So integration of powers of sines and cosines. Common thing to do with this, since it's an even power cosine, we would write it 1 plus cosine 2 theta over 2 d theta. The next step, the integral, well, you'll notice the 2's, these just cancel. So one of these terms is the integral of d theta, which is theta. I'll deal with that in a minute. Plus the next one is going to be the integral cosine 2 theta d theta, right? Plus a constant because I've now integrated. So this is going to equal theta plus, now the integral of cosine 2 theta is sine of 2 theta over 2, again, plus our constant, equals theta plus, now sine of 2 theta can be rewritten 2 sine theta cosine theta. Again, that's over 2, right? Plus a constant. The 2's cancel. So what we end up with is theta plus, and I'm going to shorthand this, sine theta cosine theta plus a constant. Now, we've got to get this back to in terms of x. I need some more room to do that, so I'm just going to kind of take a moment here and let the viewer maybe take a picture or just pause this and maybe see if there's anything there are questions about for later, but I'm going to take a moment here and get rid of this to make some more room. Now, I don't need this anymore. Just going to get rid of this because I need some more room here. Okay, so now what we have, we got this theta plus sine theta cosine theta over 2. We look to here, to our substitution here, to sub this back in terms of x. Now, since x is equal to secant theta, I'm going to rewrite that. Cosine theta is therefore equal to 1 over x, because secant is 1 over cosine. And what this will allow me to do is draw myself a triangle. Here's theta, an angle in that triangle. Cosine, remember, is adjacent over hypotenuse. So in this triangle, this is a 1, this is an x. This, I'm just going to call it d for a moment, we can find by Pythagorean theorem, because 1 squared plus d squared is equal to x squared, by, again, Pythagorean theorem. If we solve this for d, we get square root of x squared plus 1. So now, I'm going to put OI, which if you had me for class or seen some of my integration videos, stands for original integral equals, okay, theta, and I'm going to get that right from here. If I solve for theta, I get the inverse cosine of 1 over x plus sine theta cosine theta. So as I look over here now, here's theta. Sine theta is opposite over hypotenuse, so that's going to be square root of x squared plus 1 over x times cosine theta. Cosine is adjacent over hypotenuse, so that's going to be times 1 over x. And I put plus a constant, and I'm going to call that constant C2 here. Go back and put a 1 on this, because this constant came from the integral previously, which is not technically equal to the original integral. And again, that's a subtlety that's not, I think, super duper important. But these are in fact technically different constants. So if you want to just put a C1 or just a C here, in my class I'm okay with that. I'm not going to take points here. I'll just make a comment on that. But anyway, there's our original integral. This integral, the original integral, should equal that expression right there. I hope this example helps. Have a great day.